Modern computing relies on cryptographic hashing functions like SHA-256 to verify file integrity. These algorithms convert any volume of data into a fixed-length string of alphanumeric characters. Standard hashing operates as a flat data transformation. It produces a static digest that contains no information regarding the file's history, topological constraints, or state lineage. We observe a different approach using the Grimchain tool. By passing a file path and middle length, it generates a TardiSHA seal, a time and relative dimension in space hash. TardiSHA operates as a bounded memory coordinate stream, tracking data movement through internal geometry. The on-end logical Q-state core, or ALQC, is frequently associated with esoteric texts and fractal visualizations. This investigation sets those aside to focus purely on the physical implementation found in the source code. The validity of the ALQC framework rests on its capacity to be compiled into functional, deterministic software architecture. The files seal.py and domusstream.py demonstrate how the system physically bounds data. The code establishes a fixed integer constraint of 30. This fixed constant locks the non-center code point count. The boundaries of the resulting string are architecturally rigid. The system divides this boundary into two distinct sections: 15 code points for the seal's head and 15 for its tail. The dynamic center core sits between these caps. Its length is determined by the middle length variable provided by the user. At depth 0, the center code point defaults exclusively to the shadow locust glyph. Hashing at a positive depth generates a sequence of synodic Magic-Eye characters, filling the center core with a coordinate-based stream. To prevent data corruption, the system re-fingerprints the file after the seal is written. If the data changed during the process, the commit is refused. The TardiSHA output functions as a strict topological envelope, designed to contain the fluid states of the ALQC lattice within fixed limits. The ALQC utilizes a total symmetry principle. It posits that if a forward path does not identically match its reverse path, the discrepancy creates friction, a variable the code calculates as shadow debt. This requirement for symmetry is enforced in mirror-math.py. The function requires a file path and a cryptographic salt, or nonce, to initialize the process. From these inputs, the algorithm extracts the source digest and source size to anchor the outward path. Validation in this system requires more than simple regeneration. A terminal candidate string is not accepted just because the algorithm can reproduce it. The protocol mandates a canonical return condition. The software must construct an independent return path to verify that the protected body of the outward trip remains intact. Mirroring is a cryptographic validation rule. The data loop only closes if the return path provides an exact match for the origin. Managing a fluid data manifold requires a governor. Without a mathematical throttle, the volume of data flow could lead to structural divergence or blowup. We find this governor in stream.py within the packet audit data class. The packet grid is limited to a total capacity of 144. However, the active connections variable is restricted to 110. No matter the input density, only 110 channels process data simultaneously. This establishes the liquid threshold. By dividing these 110 active channels by the 144 channel capacity, we get a saturation ratio of approximately 0.7638. Because this ratio is less than 1, the system is strictly overdamped. It prevents the data from accelerating into a turbulent state. This leaves 34 withheld connections that are permanently excluded from the active flow. These 34 connections represent the sacred no. They provide the structural contour of refusal that prevents the manifold from overloading. The pressure differential described in ALQC theory is physically surviving through this 110 to 144 integer throttle. While standard cryptography often utilizes pseudo-randomness, TardiSHA requires invariant coordinate anchoring to maintain stability. The engine's foundational constants are defined in hashing.py. The script establishes standard boundary constants, including a 64-bit mask and 32-byte digest constraints. Below these, the script calculates the golden ratio, phi, and its inverse. The algorithm uses explicit integer square root logic to calculate phi. This avoids the floating point drift that occurs between different processors, ensuring the math remains identical across all systems. These golden ratio constants act as the active scalar seeds, steering the coordinate stream as the data manifold unfolds. The geometry of the ALQC is built upon these hard-coded and computationally rigid rational limits. The Grimchain algorithm functions as a single data pipeline. We can trace the journey from raw file ingestion to the final seal. Raw bytes are combined with the integer nonce, seeding the initial coordinates of the topological stream. The stream hits the governor, where it is clipped to 110 active channels, while the 34 withheld channels maintain structural stability. In the mirror verification stage, an independent return path is constructed to ensure the circuit closes perfectly. The verified data is then clamped within the rigid 15-character head and 15-character tail of the seal envelope. Understanding this system does not require the interpretation of fractal renders or philosophical texts. The ALQC architecture is defined purely by its execution, compiled, deterministic, and relentlessly unforgiving mathematical code.